So today is lecture 26. Okay, so what did we do last time? Last time we were doing tensor methods for SO and SO groups, right? So far we have seen how to build up representations of bigger representation from the vector representation. So the vector representation, they were n-dimensional. And these are the vector representations. And we saw how to build up bigger representation from vector representations. We also saw SO1, 3 as type of representations. And there, this was mu went from 1 to 3. And there were also vector representations. And we saw that if you took two vector representations and consider the tensor product, then we get an anti-symmetric representation. And then we have a symmetric but trace-free representation and a scalar representation, which represents the trace part. So F mu nu, this was some kind of anti-symmetric representation. This was a 6-dimensional representation of SO1, 3. We say that it's 6 of SO1, 3. If the context is clear, we just say 6. This was a 6 of SO1, 3. And T mu nu, this was symmetric as well as trace-free. That meant that, that the trace part is computed like this. So this is trace-free, and that is going to be A9 of SO1, 3. Okay. And then the trace part is T tilde, and that's going to be A1 of SO1, 3. Okay. We might have seen like the SO versions of these, but these are essentially the same thing. Okay. And V mu upstairs and V mu downstairs are both the same representation. And we can go from one to the other by using one of the invariant tensors of the representation. And we saw that eta mu nu, that was an invariant tensor. So if I contracted with this guy, I get this guy. So they are essentially equivalent representations. Okay, so this is just a recap before we discuss today's discussion is the SUN tensor methods. Okay. So are there any questions so far?
What does it mean for something to be a vector representation?
So yeah, here what it means is that this is a vector representation. So for example, if I took SO3, right, and then I took the 3-dimensional position vectors X, then the rotations, then the action of SO3. For the action of SO3 on X is R acting on X, right? So this is the vector representation because this guy is a vector, right? So similarly, if I have a vector under a Lorentz transformation, this vector will go like lambda mu nu, okay? And because this is one index, it's called a vector representation. Okay, whereas this is a tensor representation because under Lorentz transformation, F mu nu will go to lambda mu alpha, lambda mu beta, F of alpha beta. And then T mu nu will go to lambda mu alpha. So this is alpha. Lambda mu beta T alpha beta. So these are both tensor representations. Okay, and then, T on the other hand, we'll just go to T. And this is a and this is a scalar representation. Okay, Saif, is that clear?
Yeah, that makes sense.
Okay. So for the SO groups, the orthogonal groups, you build up bigger representation by tensoring the vector representation, the fundamental representation, and then you decompose those in terms of irreducible representation. So this is what we do. We are tensoring, this is a tensor product on the left side. So this is a tensor product of fundamental, like the basic irreducible representation. And of course, the product is not irreducible, but it decomposes as a direct sum of a bunch of irreducible representation. And the whole game of group theory, when we're talking about application to, say, particle physics, is this. Given some product like this, what could be the, what are these guys? And we'll see an example of this today. And you already know examples, which I'll point out.